welcome back. It's been a week. I offered to answer questions about your homework via email, and I got none. So that means either it's going exceedingly well, or it's not going. So would anyone like to ask any questions at this point? Yes, good. Okay, Heather and then Mayumi. Depends on how many models you're fitting. If there's more than maybe 3, then a table will help. Otherwise, you can just put them in the sentence. Your call. All right. Yes?
So, mine doesn't have, reverse and not reverse.
Mm-hmm.
So I'm going to just, after running a simple one-factor model, I thought I needed to do voodoo modification.
They may help send you into a new direction, yes.
So one-factor model ended up the p-value of 0.2 something.
For the chi-square?
RMSEA.
RMSEA is...
Chi-square p-value is...
Yeah, it always is. Don't worry about that. What is RMSEA?
RMSEA p-value is 0.29.
Okay, so you're within striking distance of something that's close fit.
Yeah.
Mm-hmm.
So, but I move on. I thought I needed to do something.
Yes, so the next step is not necessarily to fit 2 factors.
Oh, okay.
The next step is to look at the pattern of misfit, and that's given by the normalized residuals as well as the voodoo. The voodoo is capitalizing on the normalized residuals. The voodoo, if you're fitting a 1-factor model, will only suggest error covariances. It will not suggest new factors. It will not suggest a new structure. Your job then is to look for patterns in the misfit. Items that want to be more together are indicated by positive normalized residuals. Items that want to be less together are negative. And see if there's commonalities in terms of the content of what the items are asking, how they're asking it. For instance, if they refer to me versus you, or if they have a common stem, things like that can trip people up, especially if they're answering in a hurry, not very carefully. So the idea then is to look for whether there's potentially a different factor structure or potentially just 1 or 2 additional relationships among the items that would be easiest to justify in terms of error covariances that would be expected even if you hadn't looked at the voodoo.
Oh, okay. So I will just, I got stuck at the voodoo.
Mm-hmm.
I'm going to move on to normalized residual.
Yes.
Inter-item variance.
So what I don't want to see is blindly following the voodoo. So if the voodoo says things that make no sense, tell me that. The biggest change, improvement in model fit, would come from allowing these 2 items' residuals to covary, but this item is this, and this item is that, and these have nothing to do with each other, and so theoretically this modification is not defendable. That would be a fine answer. The goal is not necessarily to get to good fit. The goal is to try the best you can while keeping your model defendable. And if you can't do anything better, then you write it up and turn it in. That may be the situation for some of you. It's not often that a model fits well on the first try, only if you have like 4 items. So, your question?
I have 2 items which are reverse coded.
Mm-hmm.
Do I have to change one
I would reverse code them because otherwise your factor loadings are going to be negative, and I've seen that cause estimation problems for no reason other than that. Yeah, so like if you're listing your items, you can put a star or an R or something to indicate that it's been reverse coded. That would be fine. Yes?
I had an item that had a non-significant factor loading, but then I just ran a new model and I set that factor loading to 0, and then I can still do model comparison.
Then you can, yes.
Okay.
And the model comparison then should reveal a non-significant decrease in fit from adding that constraint, right? Mm-hmm. So I would say that In theory, yes, that would mean you could dump it if you wanted to. However, it may be the case that once you fit the proper IRT or IFA model to it, the loading is different. So you might want to revisit that for homework 5 if you've decided to dump it. But yes, that is the technically correct way to decide to dump an item. Yes. Okay, your turn.
With running the code for 2 factors.
Okay. Let me pull up an example. That is okay, although you don't get a standard error for it. So it's not wrong, per se. In theory, you'll know your code is right if the answer matches what you came up with by hand. So you should end up with the same point estimate within rounding error. Let me pull up that example that had omega in the code, and we can troubleshoot it. No. So this is example 4. And apparently my computer hates me today. No, really. Okay, I give up, Adobe. You win. Okay. Here it is. All right, this is page 17 of example 4. Make that as big as I can. So you have labeled your loadings, right? Going through the steps here. So like I have L1 to L3 and L4 to L6, making sure that you have one label per loading, so you're not making them share because that changes the model, unless that's what you had intended. You don't need to worry about the intercepts for omega. You also need to worry about labeling the error variances, the item residual variances, so that's why I have E's there, 1 to 3, 4 to 6. You have to label or just put a 1 in for the factor variance. So in my formulas down here, rather than typing variance, I just typed 1 because it was yelling at me when I tried to do that, even though the label is up there. It gets confused when you try to label a parameter that's not estimated. So that might be part of the issue. If you're trying to refer to these var p and var n labels, it's like, well, that's not a thing. You just told me it was 1. I don't need to label this. The mean shouldn't matter because they're not as part of the formula. Check to see that you have this line, the new line, because new gives you permission to put something on the left of the equal sign other than a number. Otherwise, you can just say, like, the constraint is I want L3 to be 5. And you can type L3 equals 5, and that's a constraint. But if you want to make a new linear combination of your parameters, you have to define them first with new, and then make the combination. So that may be it. Otherwise, check your parentheses. Make sure that they're balanced. And it might be easiest to carve it up into sections of the formula if it gets too long or too unwieldy. And if that doesn't work, then I can either look at it at office hours or you can email it to me.
Okay. Well, I think I see what.
Okay.
I just wanted you literally
Well, no, it's non-trivial to like copy something and change every single little thing you need to change. Like this is just a starting point. But hopefully the error message you're giving you will help diagnose the problem. That's my guess as to what it is that it doesn't know what these words are. And so it's looking for a number. Sure. By the way, it's faster for me to answer emails on my phone if you just paste in your syntax into the message, because my phone doesn't know how to open IMP files, which means I have to go to my computer, and that is like more trouble than it's worth when I have a 3-year-old who's trying to kill himself, like around the house, whereas I can maybe trail with the phone and answer things periodically. So So if you want a quick answer, paste just the relevant section in the code that's broken, or paste the error message, and that will allow me to help you more quickly. Okay, other questions? That doesn't sound good. Check your data. I guess make sure that the columns are being read as numeric instead of string. So that.
So I could run the standard deviation and the mean and everything.
Okay, that's.
So it is a read as.
Yeah, I'd have to see that. I don't know what would cause that. By the way, these things, you should not be typing any of these. You should be able to paste stuff into Excel and make it look nice. If you don't know how to do that, ask, because I do not intend for you to be typing correlation tables. That is not in your best interest of time. So item total correlation should show up as part of your reliability output. Regular correlations can also show up as part of that output, or you can just run a correlation, just a standard one. Yeah. Other questions? Going once? Going twice? All right, let me know if you change your mind at any point. Office hours are after class, of course. Shut this for now. So what have we been talking about? Big picture. I'll take letters, words, gestures. IRT. What does IRT stand for? Is it a theory? As much as any other model is. Like, I don't talk about regression theory, but it's a theory. It's a theory if you put stuff into it, because it's your theory as to how the data should work, right? Give me a synonym for item response theory. Item factor analysis. Yes, IFA. They are different versions of the same idea. Different in terms of how they are expressed. It's like centimeters and inches. You can get from one to the other. What kinds of data outcomes are IRT and IFA for? Not normal. More specifically, there's a specific kind of not normal that gets used with those words. Binary is one. More generally, categorical. Yes. So categorical includes binary, ordinal, and nominal as special cases. But the idea that you have discrete values. And so this is most common in survey items where people respond using some sort of ordered category known as a Likert scale, like strongly agree, undecided, those kinds of choices. Or I do this every day, once a week, once a year, and so forth, where you have an arbitrary number assigned to some words. And the distances between these arbitrary numbers are basically irrelevant. All you know is that they're probably in order, but you can't really say definitively that the distance from 1 to 2 is the same as 2 to 3. So they really are categories. They're discrete. They're not numeric. That's what these models are for. So we have the same type of latent trait, since this is a measurement model in class. Let's review all the synonyms you know for that. So when we did confirmatory factor analysis, what was the latent trait called? Factor, or latent, there's several of those. Latent factor is one. Latent trait, latent construct, latent variable. I think that's all the latents I know. Can you think of any others? I'll also take true score from the world of classical test theory. And now what is it called in IRT land? Theta. Always. Someone decided this in like 1940, and it has been theta ever since. I just go with the flow. So theta is still responsible for causing the responses to these items. What's the catch, though? We have to change two different things about our factor model to make it work for discrete items. What are we going to predict? Are we going to predict whether you got a 0 or a 1 directly? Or predict some transformation of it instead? Starts with an L. Logit. Yes, we are transforming the predicted outcome into a different space that is continuous. And so far you know of two different metrics in which we can do this. One is our friend Logit, which is, I need to do my little conduct. Ready? The log of the odds of the probability of a 1. Logits take probability of a 1 and turn it into something that is continuous, unbounded, and symmetric at a probability of 50-50, which corresponds to a logit of 0. So I can predict a 1-unit change in the logit as a function of a 1-unit change in my factor forever and ever and ever and ever. But the highest probability that I can get is 1. It asymptotes at 1, and actually we'll never quite get there. Likewise, if my factor decreases, I can predict a 1-unit decrease per unit change in the factor down, 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 and the lowest it goes is 0 for probability. So that is called a link function, to go from probability to logits. What's it called to go backwards from logits to probability? Inverse link. Or I call it unlogit, or back translate. You'll find me saying those things instead of inverse link, because that's the way I think about it. Another metric that does the same thing is our friend probit. I don't have a conductor thing for that, but I would do something like the probit is the z-score that corresponds to the probability of a 1. How's that? That works. So probit and logit do the same thing. A z-score is continuous, unbounded, and symmetric at 0, which is 50-50. Z-scores go on forever, but their probabilities that are implied by them do not. Probit has a special name in the IRT world. Do you remember what it is? I mentioned this once. Those of you who've had IRT, let's see, did you take IRT? What are probits called in IRT? Ogive. Yes, an ogive curve is the probit. What's the difference between probit and logit? 1.7. That's it. They're on different scales. So probit times 1.7 gives you coefficients in the logit metric. That's it. So it doesn't matter which one you pick. So when you are doing these models with full information maximum likelihood, which is all we've talked about thus far, I believe, you get your choice of logit or probit, and it doesn't matter what you pick. The model is just on a different scale. Once we switch estimators, which I think we may get to by the end of today, and limited information, you're stuck with probit. You don't get logits. So that's why it's important that you know each of these things so that you can figure out what scale your model is in based on the other choices that you've made. So that's one way that these models differ in the use of a link. So we're not transforming the data, we're transforming the outcome to be predicted by the model. So when you say link equals logit, the program does that for you. You don't have to read in anything other than the categorical responses you started with. The other way that these are different than CFA models for normal responses. What else is different? The distribution, the conditional distribution, meaning the distribution of the item responses after controlling for theta is some kind of not normal. And in these models, it's going to be one of two kinds. It's either Bernoulli, if it's binary, or multinomial, which is basically like binary if you have more than two categories. So they're both categorical distributions. Neither one of them has variance as a separately estimated parameter. Variance is determined. Variance in binary data is the probability of a 1 times the probability of a 0. So we don't have a separately estimated residual variance per item because it's determined by the mean and it's non-constant. Doesn't mean the item works perfectly. It just means that we don't need to estimate it because we know what it is once we know what each person's predicted item response is going to be, the probability of a 1. So we switch up what we're predicting. We're predicting a logit or a probit instead of the response directly. And we switch up the distribution we're assuming that our responses take into something that's not normal, something that actually matches what the responses could be. So if you have binary data, you can only have 0 or 1. Bernoulli is perfect for that. If you have, say, categorical data of 1, 2, 3, 4, 5, multinomial is perfect for that. So those are really the only choices that are available to you. They're pretty much determined. Once we get into other kinds of not normal data, which I'm not sure if we're going to get to do because I have to go to jury duty, just saying, then those are other choices you have to make. Yes, November 5th, I'm scheduled for jury duty instead of this class. I'm very unhappy about this state of Kansas. But not that anyone's listening that cares, but I just thought I'd mention that.
Quick question about normal distribution. So I did the homework using 6 items from 2 different factors separately. So the one factor I have is respect for authority. That one, they're pretty much perfectly normally distributed. Like these histograms are perfect. The physical harm is almost completely skewed with like peak at the right and it's just like half a normal. Is that still considered normally distributed?
No.
Okay.
Nope, I would call that skewed.
Okay.
And the problem there is not so much the lack of normality, but the assumption of linearity. When all your people are piled at one end of your scale, the linear model is going to want to keep predicting responses beyond the pile, but those are impossible.
Right. So in my final thing, I want to have all of the factors. So some of my factors will be normally distributed, some won't.
So important distinction. Factors are always normally distributed. Always. That's not a choice you get.
Yeah, so the items.
The items.
In my factor.
Yes, the item responses specifically are not normal in your case, but you're pretending they are. So what will be interesting to see is when you fit the right model, when you fit the IFA model in homework 5, how your conclusions about fit and goodness of an item change as a function of taking into account that you can't predict scores that go on forever and ever because you only have 5 response options or whatever it is.
And so I can do CSA or IFA. Is IFA just a more sophisticated technique?
It's not. It's a technique of so the world is measurement models, right? Broadly construed. And in the same way that you can have a regression model that predicts a continuous outcome or a count outcome or a binary outcome, you can have a measurement model that does. It's more complicated in the sense that you have to understand not just the linear model part, but the link and the alternative distribution and its characteristics. It's not more complicated to estimate until you get to models with more than maybe 2 factors. And that's actually what we're on tap to talk about today, is how much of a pain full information maximum likelihood is in the world of IRT and IFA. So it's more complicated to estimate. It's not necessarily fancier or otherwise. It's just that's what you need for that kind of data.
What kind of data?
Categorical data.
Okay.
Bounded data, broadly construed, discrete data, which is what most of you actually have with the exception of Mayumi, who is something that's approximating continuous but not normal. She's got a pile at the end still, but she's got more categories.
So with I have to use IFA, CFA.
CFA at best will be a decent approximation of what the IFA model should have been.
Okay. So in all the research I read on the subject, they use CFA.
Yes.
So will I have it's like be more sophisticated if I use IFA?
It will be more right.
Okay.
But that's where you have to tread very carefully in describing what's been done in previous research. It's not that they were wrong. It's that you're taking this in a different direction with the following advantages. They're never wrong. You're just making benefits. Yes. But yeah, all of you probably shouldn't be doing CFA. Welcome to the world. Why do people do CFA? Because IRT and IFA is very hard when you have more than one factor. That's why. Until you switch to limited information, which comes with its own problems. And so that's the trade-off that I think we may get to today. We'll see. So yes, no matter what kind of measurement model you're fitting, theta, latent trait, latent factor, etc., is normal. There are very few options in software that have something other than normal. I think M+ allows skew normal, and you can also have it be discrete, like in latent classes or or diagnostic classification models, but there are no other kinds of thetas. They're normal, forever and ever. Other questions? So do you want to talk model parameters? So let me get a terminology thing here. I like my picture. I'm going to pull that up. So the IRT models look nothing like the models that you're used to seeing. So I'm starting on slide 54 to remind you of the differences in terminology and representation. So the first line here, linear regression and CFA. Even though CFA has different symbols, so we have that U-looking thing for beta 0, and we have lambda for beta 1, they map onto each other perfectly. So beta 0, or the intercept, I guess, is that mu? Greek people? Yeah. Excuse me. People who understand Greek symbols. I only know like 3 of them by name, but I'm going to go with U-looking thing for that. So U-looking thing slash beta 0 mean the same thing. That's an intercept. Expected outcome when your factor or your predictor, broadly construed, is 0. Lambda, or beta 1, slope, loading. Change in the expected response for 1 unit change in your predictor slash factor. Got it. Even if we switch the model to be a logistic regression type model, where the expected response is now the logit, or the log of the odds of the probability of a 1, beta 0 is the expected logit when x is 0, and beta 1 is the change in the logit for 1 unit change in x. So even though E has gone away and we added logit to the left-hand side, everything still functions the way we're used to seeing it. In contrast, the way people write measurement models for binary outcomes looks really different. It's still logit on the left-hand side, but then we have A, theta, and B. So A is discrimination. That's the analog to slope. B is difficulty. Theta is theta. And notice subtraction here, the minus sign. That makes it so B is actually difficulty, so that higher B values signify items that you have a lower chance of getting correct. It takes more of theta to answer a harder B item. So B is defined as the trait value at which you have a 50-50 shot of getting it right. So if B is 2, that means it takes a theta of 2 to have a 50-50 shot. If you have a theta greater than 2, you have a better than 50-50 shot. If you have a theta less than 2, less than 50-50. A is the slope at that B location on the curve when you're plotting it in probability, or it's just a linear slope when you plot it in logits. So, quick picture here. Back to the beginning to show a picture. A would be the slope at the 50-50 mark. If you're plotting it in terms of probability, it's a nonlinear slope. When you translate that probability into logits, A is a linear slope. So it's sufficient just to say slope because it is a constant slope in terms of logits, which is how the model is phrased. When you back translate logits into probability, it's a nonlinear slope, and then it's this one. It's the one at the 50-50 mark. So if you see models expressed in terms of these A's, B's, that's called a 2-parameter logistic model. If you assume each item has the same A, that's the 1-parameter version. The model where each item has the same A has another special name. Starts with an R. It's a dude. Rosh, yes. A model where there's no differences in A across items is a Rosh model. Is a tau equivalence model. Is an every item is equally good as another model. We call it a 1PL in the world of IRT. Once you add a different A for each item, that's called a 2PL. If you add a lower asymptote, that's 3PL. Upper asymptote, that's 4PL. But this thing, I think we can all agree, looks basically nothing like all the other models on the page. So if you express your item parameters in A's and B's, you would call that IRT. But you can algebraically rearrange this into something that looks a lot more like either a logistic regression model or its measurement counterpart for CFA. Always this thing moves over. I will never know why. There. So because the IRT model has that minus sign, we have to rearrange the intercept to become backwards too. Just like B is really difficulty, we need the intercept to become something that's really difficulty. And so minus 1 times the intercept mu is the threshold. So that's that tau looking thing there. So minus tau plus lambda f, that's our model. So we replace the intercept with this threshold thing to keep the direction of what B means consistent across these different versions of the model. So whereas the intercept is the expected logit of a response of 1 when x is 0, the threshold is the expected logit of a response of 0 instead. We have to stick the minus sign back in to make it look like the regular CFA equation, though. Then we get to the conversion, which is shown here. So the threshold is A times B. The loading is A. I do not expect you to memorize these. I'm going to give you a spreadsheet that you can use to plug one version in and get the other, and I'm going to give you M+ code to make it compute it. All I want you to know is that these things are synonymous. A is to loading as B is to intercept. B and intercept are not exactly the same thing, though, because they are both in reference to a different thing of reference of 0. So here is the picture that I wanted to show. This is slide 59. So I have an item characteristic curve for an example item here, where the item has an estimated A of 4.3. Given that our theta variance in this model is 1, the loading is the same as A. Otherwise, the A gets rescaled as a function of the theta variance. That's another reason why it's convenient to have theta have a z-score distribution with mean 0, variance 1. So that A is the slope at the B value, which in this case is minus 0.38. So just below the average value of theta is where you would have a 50-50 shot of getting this item right. So it takes just under average theta to have a 50-50 shot. So B1 is relative to a logit of 0. That corresponds to 50-50. So B1 is where the logit is 0. Intercept, right here, is the predicted logit when theta is 0. So in this case, the predicted logit at theta 0 works out to be 1.63. So if I have an intercept of 1.6, that doesn't really tell me directly how hard that item is, because that tells me what the predicted logit is for somebody with average ability. If I want to spin that around and say, well, how hard is the item, to me, the B value is way more intuitive. Is it a hard item? No, it's actually on the lower side of difficulty. It's a below average difficulty item. It only takes minus 3 standard deviations to have a logit of 0. Minus 0.3, yes, excuse me. Minus 0.3, yes, where the blue line is. So on the curve, the intersection of that blue dotted line, that's where B is. On the curve, the intersection with the red dotted line, that's where the intercept is. So they're telling you the same kind of thing. They're telling you about location, but it's relative to a different reference point. Blue, B, is relative to when the logit is 0. Red is relative to when theta is 0. And to keep the direction of B consistent with mu, you have to multiply it by -1, and that becomes the threshold. So whereas the intercept, this is the predicted logit of y equals 1 when theta is 0 is 1.6. Logits are symmetric. So that means the predicted logit of y equals 0 is -1.6. And so on your output, depending on your program, you will either get an A and a B, or you will get a loading and an intercept, or you will get a loading and a threshold. Job security, people. I want you to know which one you've got. And hopefully looking at the documentation of the program can help you figure it out. So even though M+ directly estimates loadings and thresholds, I find it far more convenient to rearrange them into A's and B's. A's and B's to me are more meaningful and easier to convey to people, but it really is 6 to 1, half a dozen of the other. If you're used to writing for audiences that are used to factor analysis, right? You're doing item factor analysis, you need to give them loadings, and you can pick either intercepts or thresholds. Even if M+ gives you a threshold, take the minus sign off, or add one, right? Threshold times -1 is intercept. Intercept times -1 is threshold. Take your pick. I go with loadings and intercepts, because that's what most people understand in terms of CFA. If you're in education, if you're writing for audiences that are used to things like IRT or ROSH, give them A's and B's. You can get from one to the other in any program. All right.
One more time. People at CFA, what would you?
CFA, give them this right here. This is slide 60. Give them intercepts and loadings. If you're used to IRT or ROSH, give them A's and B's. If you want to cover your bases, make a table with all of them. I personally find B's easier to talk about and more useful in terms of diagnostic information about the scale than intercepts, but whatever. It's up to you. Do you want to look back at the M+ example, or are you ready to move on? Take a vote? Look back at M+ and some numbers, or move on to estimation? No one wants estimation. Okay, one more time. Look back. 1, 2, 3, 4, 5. Go on. Oh, I think it's like a tie. All right, we'll do both. We'll do this quickly. How's that? So M+ gives you thresholds and loadings directly. No, office, I don't want you to update right now. Thanks, I'm teaching. How does it know every time? Well, fine, we'll just work around the stupid little window. So the name of my factor in my example is Instrumental Activities of Daily Living. These are 7 items that older adults need to be able to do in order to live independently. I've got a sample of 635 people who answered 7 questions. So by gives me my factor loadings. In this case, this is what's known as the 2PL. These are binary items. Each item gets its own loading. In contrast to the right-hand side, in which I've added a single word loading, that means I gave one label to 7 different parameters. That's me forcing them to be the same. So I'm saying make all 7 items share one loading. That's the 1PL or the ROSH model. The next line, I don't actually have to type that it's a default, but I want you to know how to refer to it. These are thresholds. $1 refers to the first transition in these binary items between an answer of 0 and an answer of 1. There is no other transition. But if we had, say, 0, 1, 2, then I would need to ask for $1s and $2s for each item because there'd be 2 transitions. Those are all being estimated separately. So because we're estimating a loading for each item and a threshold for each item, the model is identified by fixing the latent trait mean to 0 in brackets and the latent trait variance to 1. There is no residual variance, and therefore there are no possible residual covariances directly in these models. You can do -2 log likelihood difference to see if the 2PL is better than the 1PL. In this case, it was significant. We will see momentarily in talking about estimation why these Pearson chi-square things are useless, except in cases of very big samples and very few items. Here are all the different solutions that we get out of M+. So first, on the left-hand side, this is what it's estimating directly, loadings and thresholds. So it will just call it IADL by. I added those words to help you. So this is the change in the logit for a 1-unit change in theta. The threshold is the expected logit of y equals 0 when theta equals 0. And you remember how to turn this into an intercept? Watch carefully. Ta-da! Threshold times -1 is intercept. So if you don't want to have to explain what a threshold is, don't. The intercept then is the expected logit of y equals 1 when theta is 0 instead. It gives you standardized loadings as well as standardized thresholds. I'm going to stop after this handout and even reporting this information, because what can I conclude about these standardized loadings? Like this one right here, number 4 has a standardized loading of 0.97. Does that mean it's a good item? That's pretty darn high, right? Almost perfect. Can I just say it's good? No? Do I have to make a caveat? At what point, right? And this is why I don't think that the thresholds are as useful as B's, because it's at the point of B that it's good. So you have to know where B is to be able to say at what point this is an informative item. So here, in binary data, M+, no! First jury duty, and now my laptop hates me. That's all right. I have this handout memorized. M+ gives you the A's and the B's that go with these. You don't even have to ask for them. They just do it. They also do the same thing for the partial credit model, and they don't do the same thing for other ones. So I'll teach you how to do it for other ones, but for now they give them this. So you'll notice the A's that it gives, the discriminations, in the right-hand column. They look suspiciously similar to the loadings, right? They're the same because theta variance is 1. They will not be the same if theta variance is not 1 because they re-standardize the A's and B's relative to a theta variance of 1. The B's, then, are not the same as the intercepts or thresholds because they are reflecting a different interpretation. They are the amount, they are the trait location at which the logit is 0, or at which point you have a 50-50 shot of a 1. Thank you, laptop. And it's like, welcome back. Like, eh. So I did some math for you to try and show you how to use the numbers in here. So in an IFA model, it would be -1 times the threshold. So that's why it's a positive number here, plus loading times theta. That's what gives you your predicted logit. In IRT, it's A. So there's my loading / A parameter times theta minus B. So item, what was that super good item? Let's find that one. That was number 4. Item 4 is the purple one. Can you see that right there? Purple is super steep. It's the steepest one. So the standardized loading is conveying how discriminating it is. The catch is that it's only discriminating within its realm of where B is. So it's a great item for people with a theta of about, I'll go with maybe -1 standard deviation up to 0. That's where it's informative, centered at its B location. So where is B for item 4? Let's find that. It is over yonder under item difficulty. Yeah, minus 0.4. So it looks like from just eyeballing this, from about here, maybe minus 0.8 or so, up to here, that looks like a theta of 0. It's a super duper discriminating item. However, item 4 is useless if your trait is minus 2. Item 4 is useless if your trait is 2. In contrast, if we look at the standardized loading for item 7 here, it's the lowest one. It's 0.76, which is still pretty good. And if you were going to make a short form of this test, perhaps, you might be tempted to get rid of this one because it's the lowest. However, item 7 is out here. Even though it is relatively less steep, it covers an area that is currently uncovered by other items. So if you were to drop item 7, you'd be sacrificing measurement of super low theta people because there's nothing else that would discriminate them. This combination of having all of these curves centered below 0 creates a test information function that looks like this. Information over information plus 1 is reliability. So I can plot reliability instead, which I almost always do because it's way more informative. And you can see that this is a good test to discriminate people in terms of how capable they are of living independently from about, I'd say, minus 1.8 theta up to about, 0.2. It's good at identifying low people. It's terrible at identifying capable people. Depending on what you're giving the test for, that may not be a problem. If you want to increase your measurement of people on the high side, though, you've got two choices. One of them would be to add more difficult items, things that even highly capable people would have to say, no, I can't do that. The other would be to expand the choices. Right now, we're using a binary metric of nope or yep. How about maybe or sometimes? So there's actually a 4-point version of this test that we'll look at next. So those are the two options you have for expanding the range over which you have decent reliability, adding items that cover that new range where you're missing, or adding response options that would dip into that. And so we'll talk more about that later. So because of this reliability function, the thetas that we get, these are the best guess as to what each person's theta is, the mean of their theta distribution. You see a giant pile. Those are all the people who can do everything. There's no way to differentiate them. So even though theta is supposed to be normal, theoretically, it ain't. And it can't be with these 7 items in this sample. All right. So those of you who wanted a review, does that help? Other questions before we move on? Okay. So why do I have to talk about estimation? I honestly don't like it very much either, to be honest with you, but here's why. Because in the world, these two different versions of the model, the IRT is AB and the IFA is loading and threshold, those are usually confounded with a choice in estimation. So to be absolutely clear when you write up what you've done, you need to specify which type of estimation you've used. And within the world of M+, without going into the Bayes Kool-Aid, there are two main kinds. There's limited information and there's full. Historically, IRT AB corresponds to full information, and that's what I've shown you so far. That's the same thing that we did in CFA. Full information means you use all the original data. The alternative is what's known as limited information, and historically this goes with IFA, and I believe is actually the default in M+, limited information. So this is some kind of weighted least squares. The idea behind limited information is that it uses a summary of the data to estimate the model instead of the original data. It causes some compromises because of that, but it works much faster and is more stable in smaller samples. So because of this distinction, I want you to understand a little bit about what's going to happen when you pick one versus the other. To foreshadow, when you pick full information, you get all the nice things about missing at random in terms of missing responses, but you don't get any decent information about global model fit. It's very hard to do, and most people ignore it in the world of IRT. They do things like item fit and person fit, which are various things that I'm not going to teach you because they're kind of voodoo. In contrast, limited information, if you have any missing responses, you have to assume they're missing completely at random because the summary doesn't know where it came from. All you have is a summary of your items. You don't have the original data at that point. But on the plus side, because you now have a summary that's going to become like H1, our original covariance matrix, we get model fit again. So what I end up doing in practice with these models oftentimes is starting with limited information because it's easier to assess fit that way and it runs very quickly. And once I'm happy with the model, re-estimating it in full information maximum likelihood to get the best version of the parameters as well as the trait estimates if I'm interested in those. So you kind of have to know a little bit about both. So here's the deal with full information maximum likelihood. We'll pick up on 63. So questions before we dive in. There will be some stories in it, I promise. The stories help, I think. So let's say that we're going to estimate the model for these example data. What all do we have to estimate? And when I say estimate, I mean find answers for. I've got 7 either A's or loadings, take your pick, and I've got 7 either B's or thresholds or intercepts, take your pick. So that's 14 things, 14 parameters. I don't have to find the mean or the variance of theta because I've set that to 0 or 1 respectively for identification. Now likewise, what each person's theta is not an estimated parameter. That's not one of the things we're trying to find. However, the fact that we don't know what they are is going to cause this estimation to become much more cumbersome, take longer, and break down more quickly than in the world of multivariate normal. So in your Embretson and Rees chapters, they talk about a few older methods of estimation, so I'll bring those up just in passing. People don't really do this anymore. There's conditional maximum likelihood, in which case you substitute the sum score for the theta in estimation. That only works if you have a Roche-type model where each item has equal discrimination. There's also joint ML, where you pretend the thetas are fixed effects. That breaks down because then the more people you have, the more things you have to estimate, and that is not a good deal. So the gold standard then in the world of maximum likelihood is what's known as marginal maximum likelihood. So you'll see, these are words that you will see that all go together. There's full information maximum likelihood, full information marginal maximum likelihood. There is numeric integration, and there is adaptive Gaussian quadrature. File all of those words under the same umbrella. That means uses all the data and requires calculus to pull off. Not you, the machine. So that's what we're talking about. It is the same idea of building a height that describes each person's data that we did in CFA. The only catch is that what was the formula for height that we used in CFA? What was it based on? What kind of items were we supposed to have in CFA? Continuous and normal, yeah. The reason that we say CFA assumes normally distributed items is because we are using the normal distribution to calculate height. More specifically, multivariate normal, because we're calculating the joint height of a person's set of item responses. We're switching out a new distribution. We're using multivariate Bernoulli for this to do, but it's still the same idea, height. That's what we're after. We're trying to maximize the height of the entire sample set of data. And to do that, we're going to end up multiplying people's likelihood values, their heights together, or adding up their log versions, which means we're assuming independence. So it's still the case that we're assuming people are independent, just like we did in CFA, and we're assuming local independence as well, meaning that the items are unrelated after controlling for whatever traits are in your model. So here is an overview of how this works. You get some sort of start values. You got to start somewhere. So you might start with the classical test theory values. So you might take the sample's probability of a 1, that p-value, and work from there. Ding, exactly. So the model itself, the IRT model, no, hey, I better be up to date. Goodness. Can I just have an hour without you updating yourself without my permission? Windows. Right now my husband is laughing hysterically somewhere, thinking, you need to go to Mac. He tells me that at least once a day. You won't go back. Once you go Mac, you don't go back. And I keep saying no, but if you're going to keep doing this, we're going to have to talk. But I digress. So regardless of whether you're talking IRT or IFA, the model directly tells you what the probability of a 1 is if you know A, B, and theta, or if you know theta, threshold, and loading. Right? You know the model gives you that. We just have to figure out what those things are. So we take the predicted probability and we throw them into this height formula where it's the product across items of whether or not the probability that they got a 1 if that's what they got, or the probability that they got a 0 if that's what they got. And we multiply all of those together because the items are supposed to be independent after controlling for theta. So whereas we know what our current best guess is for what the A's and B's are, we don't know what each person's theta is. There's no way we can know that. So this process of adaptive Gaussian quadrature or numeric integration requires trying on thetas for people. And we then summarize the results of that trying on process. And that is what's known as integration. For those of you who remember calculus, anybody? A few people? We are integrating the area under the curve. You'll be like, got it, great. For the rest of us, it's like, I haven't seen that since I was 17. Like, never fear, I've got an analogy for you. So, quadrature, that is a new word. It means cutting up a continuous distribution into rectangles. The number of quadrature points that you are using with which to do this, so this is our theta distribution cut up into rectangles, is set by the program or by you. So for instance, M+ has a default of 15 points of quadrature. It's going to cut up a theta distribution into 15 points. So we know what theta's distribution is, right? It has a mean of 0 and a variance of 1. So it will pick the 15 intervals and cut it up such as it is. We then try on a theta out of each of these intervals, see how likely the data is for that, try another one on, see how likely it is, try another one, try another one, try another one, and we add up the heights of all of these tries for each person. And by trying on all possible values here, all 15 possible values in this case, we don't have to know what the right theta was. We just have to know what the height was, presupposing that person's theta is the right one. We also have to know how likely it is that each person's theta is what it was tried on. So here is the math. I can give you a real-world example. So I'm wearing pants, as I noted before. After fall break, I had to actually put on, grown-up clothes again. But I'm wearing jean pants, as I call them. They're jeans that are cut like dress pants, because I hate jeans. Now, most of you are wearing jeans. I can't find a pair of jeans to fit me to save my life. I hate it. It's a debilitating experience. And every time I try, it's like I go through this process. Because I have to cross cut with size, with brand, right? And some of you are like, the girls are like, and the guys are like, no. I walk over, I pick up my width and my length, and I take it to the cash register, and I'm done, right? That's what happens. And no, my husband does that, and I want to scream because it's really unfair, because women don't have coordinates, right? We get one number that's supposed to do the job for both, but that's a whole other thing. So just picture me like trying on 8 million pairs of pants through this process. And how long do you think it would take to try on 8 million pairs of pants? A really long time. Your algorithm is trying on like 1 million thetas, and it takes a really long time. So when you have only one dimension, it's not so bad. But when you have more than one dimension, that's where things get bogged down. So it goes a little something like this. Let's say that we just have an A parameter that's 1 to make the math easy. And for item 1, 73% of the sample got a 1. So let's convert that into a logit of 1 as a starting value for this item's difficulty. So that would be corresponding to a difficulty of -1, since difficulty is backwards. And item 2, 27% got this right, which corresponds to a logit of -1. That creates a B of 1. So just based on the raw numbers of the data, how many people got item 1 right and item 2 right, we get start values for B. I'm going to use a start value of 1 for A because that's a reasonable guess as well. So then we're going to compute a per-person likelihood using those item parameters and trying on, in this case, 3 possible thetas. Instead of 15, because I don't have room on my slide, we're going to do 3. We're going to try on -2, 0, and 2. So for item 1, if my theta is -2, here's my model. A, which is 1 in this case to make the math easy, theta minus B. So -2 minus a -1 gives me a predicted logit of -1. So if I got a 1, then what goes into my formula for height is 0.27, because that's what it corresponds to. If I got a 0, what goes into my formula for height is 0.73, because I know what I got. So this is just the probability that I got what I got. So if I got them both right, I would take the probability of y equals 1 for item 1 times the probability that y equals 1 for item 2, which is given by the same formula here, just substituting in a different b value. And that's my joint likelihood that I got them both right. Okay. So far, so good? So I'm just trying out a theta. Assuming that I know what b is, if I plug it into my IRT formula, that gives me the predicted logit that y equals 1. So for item 1, if I try on a theta of -2, the predicted logit that y equals 1 is -1. That corresponds to a predicted probability of a 1 of 0.27, or a predicted probability of a 0 of 0.73. Let's say, for the sake of argument, that this person that I'm trying on thetas for got both of these answers right. So I do the same thing for item 1 and item 2. I multiply the predicted probability that they got the 1 together, because items are supposed to be independent after you control for theta. That shows up in this column right here. Now let's talk about theta per se. How likely in a normal distribution would a score of -2 be? Likely or not likely? -2 standard deviations? How likely is that? Not so much, right? So we're going to downweight that likelihood as a function of how likely theta is. So if I've cut up my theta distribution into 3 rectangles here, the area that goes with -2 is going to be 5%. So I end up with a product, if I multiply those things out, of this number right here. So that's try number 1. Okay, new pair of pants. Great. Try number 2, theta equals 0. Now the predicted probability of a 1 is a 1 for item 1 and -1 for item 2. Multiply those 2 probabilities of a 1 together, since that's what I got, show up here. Now how likely is a theta of 0? Very likely. So we're going to upweight that prediction because it's likely that a theta is 0. Here's my new product. Then finally, we're going to try on +2 theta, come up with the predicted probability of a 1, which is the highest yet. As you might imagine, if I got both items right, odds are good I have an above average theta. But I have to downweight it because a theta of +2 is not very likely. So then multiply those out, and I get here. So if I take sort of the height of the -2 guess plus the height of the 0 guess plus the height of the 2 guess, I get that number. And that number reflects the total height of my pattern of item response after trying on all of the different thetas. 15 thetas in M+, 30 thetas in other programs like Bilog, I think. So I've integrated out theta from this model, which is why it's called marginal maximum likelihood. So the process of adaptive, so it's the term Gaussian quadrature is because a normal distribution is called a Gaussian curve, and normal quadrature didn't sound fancy enough, apparently. So it's adaptive Gaussian quadrature because once it figures out for each person the most likely range for your theta, it goes back and re-rectangles just that little chunk to try and get a more refined estimate. So it goes through twice, which is why it's known as adaptive. So marginal maximum likelihood, full information maximum likelihood via numeric integration or via adaptive Gaussian quadrature. All of those words go together to describe this idea of trying on thetas. So in one dimension, this isn't too bad. But what happens is that every dimension you add adds another orthogonal set of rectangles, right? So if I have 15 tries in dimension 1, and I have another 15 tries in dimension 2, and I've got to do all possible combinations, how many combinations is that? 15 times 15? 225. How about if I have a third factor? I got to do like a box in 3 dimensions here. That's 725, I believe. What's 15 to the 4th? A lot, right? So this is why the world of IRT, you'll often hear like assumes unidimensionality. Because once you get past like 1 or 2, this thing will blow up. And sometimes even M+ will just say, you don't have enough memory on your computer for that. You just asked for 8 million rectangles. I'm not doing that for you. Your laptop can't even handle Office. What are you thinking? It will give you a message and just not do it. So you can even take classes on multidimensional IRT because the idea is that the fact that you have more than one theta is just foreign when you have this much trouble estimating just the one. Whereas in CFA, it's very common that we would have more than one factor because you don't have to try on the thetas. In normal data, the theta distribution is a sufficient statistic. We don't have to integrate the thetas out to figure out the likelihood of each person's data. We just plug in the stuff into the normal distribution formula. So it's a new ball game when you get this stuff here. So it takes a long time, and it may break down, particularly in small samples. And so then this is another idea then, once we know what the items are, we go back and figure out people's thetas. It uses calculus to figure out where to go next. So this is where derivatives come into play. I'm not going to spend too much time on that, but I believe it's in your readings. So it's trying to find the flattest part of the curve at the top here, and if the derivative is positive, it knows it's on this side. If it's negative, it goes on that side. So there's a description of this in Susan's chapter. I think she does a better job explaining it than I ever could, so I will let her do it. But this is where information comes from. The second derivative of the function that describes this likelihood of each person's theta is related to the standard error. So 1 over the square root of that derivative is standard error. That's information. So that's where information comes from, is a result of this estimation process. So how do you get a theta for each person, even though you integrated them out of the likelihood, even though you just tried on a bunch of thetas and it's not a parameter? If you're just using straight up ML, you don't have possible thetas for people who have perfect response patterns. The only way you can get them is by combining ML with prior distributions. So we're actually invoking Bayes, whether people talk about it that way or not. So you end up with a theta that is some weighted mixture of the idea that theta is supposed to be normal plus your own pattern of data. So the more items you have, the less weight is given to that prior distribution, whereas the fewer items you have, the more people's thetas are squished together. But theta is not a model parameter. theta is a random effect. Each person's theta has a different standard error around it because of information. So if we go back to trying to tie this all together, this function right here, people who have thetas in this realm have the lowest standard errors. People who have thetas over here or over here have higher standard errors. So if you think about standard error as a standard deviation, we can make a best guess as to what each person's theta is, but that guess is not right. It's the mean of some distribution, the width of which is characterized by their standard error. So when you output a factor score, even though you can do so very easily in M+, and you can make pictures of them, what you're outputting is the mean of a distribution. Outputting them and treating them as perfect is wrong because we don't actually know what each person's theta is. And that's where SEM comes into play. The whole point of structural equation modeling is that we don't have to output thetas or factors. We can predict their variance, we can correlate them with other things without ever knowing what each person's theta actually is. So theta is not a model parameter. Its variance and mean are. And in this example, the predicted thetas have a variance of 0.74 when you output them. It's supposed to be 1, but it's 0.74 because it's shrunken by the normal distribution around it and the fact that there's only 7 items. So the thetas you get out are not even theoretically that have the same properties as the thetas that are in the model. So we don't want to output thetas unless we absolutely have to. We don't want to stick them in secondary models unless we absolutely have to. All right, we didn't get to weighted least squares, but that's what's coming next. So there's 3 methods of scoring. We do -2 log likelihood, you know that. Okay. And then there's fit. We get into that next. Okay. How are we doing? See, now you're wishing you didn't hear about estimation. Here's your take-home. Is full information marginal maximum likelihood fast or slow? Slow. Does it break down when you have lots of factors or not? Yes. There you go. Just take that with you. That's good enough. If anyone wants more details, you can cite anything on your reference list. Then we'll get into why there's no model fit in full information maximum likelihood next time, which will be next week. So, any other questions before we adjourn? All right, then office hours start now. Let me know if you run into any problems. Otherwise, homework 3 due via Blackboard on Friday by 11:59.